Hey there, hi there, ho there. Welcome back to Unit 6. Let's focus a little bit more on sedimentary rocks. They're going to tell the best story as far as Earth's history, kind of reviewing not necessarily the best rocks for dating, getting absolute dating using radiometric dating techniques. However, the rocks themselves tell one hell of a good story, or they tell the story of the Earth in particular locations. So we're going to dive into sedimentary rocks just a little bit more once it starts going. There it is. Okay, the reason we're talking about sedimentary rocks is that they preserve evidence of the process of surface deposits. They preserve evidence of kind of the environment in which the sediment was deposited and or the rocks formed in. And they also may contain fossils. Many sedimentary rocks contain fossils. They're the main type of rock that has fossils. You can find some in igneous rocks like we talked about last unit, but mostly sedimentary rocks. So all these things, as mentioned, give clues to the depositional environment, the type of environment that deposited the sediment that would eventually become the sedimentary rock. Depositional environments are specific to certain areas or environments. They can tell you, oh, there was a beach here. Oh, there was a desert here, based on the rock, the sediment, structures in the rock as well, all of which we'll talk about. Again, they preserve great evidence and tell a great story. So not only do they show physical and chemical evidence of an environment, but also biological processes as well. So sedimentary rocks, they're not my personal favorite. They're not much to look at, but they tell a good story. So reminder that there was a couple of different compositions when talking about sedimentary rocks. We had chemical sedimentary rocks. That can be useful when trying to figure out environmental information. For instance, limestone is deposited, the sediment that makes limestone is deposited in warm, shallow seas. So if you're looking at limestone rock, so the sediment that was deposited to create that limestone layer indicates that warm and shallow seas were in that area. Evaporate sedimentary rocks, chemical sedimentary rocks. This is when when material comes out of solution and is deposited, such as rock salt and gypsum, indicates areas where there was water, but then very high evaporation rates, meaning there was water, but then it had to evaporate real quickly. Maybe a big storm in the desert, and the water evaporated quickly. Welcome back. Sorry, I had a little snafu with my PowerPoint here. Okay, anyway, detrital sedimentary rocks made up of little pieces of detritus or sediment, broken down, weathered, and eroded rocks. So detrital rock composition tells us something about the source rocks, the rocks, where this material came from, as well as how that material was transported and deposited. So to understand with all of these, what they're trying to tell us, let's kind of break down each little characteristic. Remember grain size, especially with detrital rocks, big sediment size versus small, and what they tell us. The size of the sediment that eventually made up the sedimentary rock is an indication of the energy conditions during transportation and deposition. So high energy processes like fast moving streams, fast moving water or waves, a lot of energy there, are needed to transport bigger sedimentary pieces like gravel. So if we're looking at a conglomerate, which is a detrital sedimentary rock that must have been deposited in areas where these kind of processes prevail, because conglomerates are made up of cemented together gravel size pieces of sediment. Sand transportation always also takes high energy transportation. That's why you see it kind of at the beach. But then you have silt and clay, which are, only really need weak currents to transport them, and they accumulate under low energy conditions. Silt and clay sized particles, they don't really deposit in fast moving streams or near the beach because of that high energy material. It's just going to wash all that material away. So they usually eventually settle in low energy conditions, kind of in lakes that aren't moving all around, lagoons, or deep ocean where things are kind of calmed down. So here's a stream, and you can see it's dominated mostly by large grain-sized rocks, so gravel or higher. Beaches also high energy. That's why you see sand in the area. And then this is a plume of silt or clay. So you have a kind of a muddy river here, and it's kind of taking with it not only fresh water but sediment as well. You see near the beach, the sand stays kind of near the beach. That gets deposited in high energy environments. Where that silt and clay, those smaller particles, kind of just keep floating out into the water and kind of get deposited further out in a little bit deeper parts of the ocean where it's a little bit more calm. It's not getting that constant energy and turbulence of waves. So a reminder, gravel-sized pieces, anything bigger than 2 millimeters or so and larger, make up things like conglomerates and breccias. They are a little bit different. Sand-sized particles make sandstone. Silt and clay-sized particles can make things like shale, mudstone, siltstone. Sometimes they have different names. So grain size is one indication of an environment in which transported these things. So you can look at a sedimentary rock and so say, oh, based on how big the pieces are, this must be the sort of environment that transported and or deposited these sediments. So again, you're inferring something about the past, the environment of the past. So when we talk about rocks, we talk about first texture, usually size, distribution, shape, arrangement of pieces. But there's a subset of kind of texture, and that's sorting and rounding. They're two textural features of detrital sedimentary rocks that also, again, aid in the determining the depositional process. So sorting basically means how alike are the pieces that make up the rock? How alike are the pieces of sediment in regards to size? If the size range is not very great, if you're looking at, say, a sandstone and you look under the microscope and all the sand-sized particles that make up the sandstone are all the same size, thereabout, we say that rock is well sorted. If it has a range of class size, we say that that type of rock is poorly sorted. And those two things, again, also can indicate depositional environments. So, for example, wind has a limited ability to transport sediment. It's known as an aeolian environment. So wind can only blow little stuff, sand or below. But glaciers can carry any size particles. So glacier deposits tend to be poorly sorted because it has all kinds of different size stuff. As a glacier moves, it pushes everything and takes everything with it, small or large. Wind, again, can only really transport smaller things, so wind deposits are usually more well sorted. So when looking at sediment itself or sedimentary rocks, well sorted, right? They're all about the same size, grain material. Poorly sorted, they're all over the place. So here's an example of a glacial deposit, something called a glacial moraine. I'm assuming there was a glacier here at one point, and as that glacier pushes down and continues to move, anything it carves out and pushes out of its way gets deposited at the end of a glacier. It's called a terminal moraine. But you can see all of that stuff is different size. Big pieces, small pieces, in-between size pieces. Whereas in windy environments, aeolian environments, where you typically, if you were to get sand dunes that's in these sort of environments, the sand is pretty much all the same size. Poorly sorted, well sorted. We can also talk about the rounding of the material. It's basically how round it is. Have the sharp corners been kind of ground down so it's more round in shape? Generally, in transport of sediment, as things are kind of bumping into one another, they kind of get rounded off. Smaller particles usually stay in what's called suspension. They usually stay floating in the water, so they don't usually bump into one another. So if you're looking at smaller pieces under a microscope, they usually stay pretty sharp. But what this indicates again is just an environment, probably high energy environment, where these things are constantly battered together and just starts to smooth these things out. By the way, it also makes it a nightmare to identify minerals and rocks when they look like this. Minerals and rocks are best able to be identified when they're kind of like fresh from the ground. They haven't been through processes like this. Where do you typically find rocks that look like this? Think about it. Where do you typically find rocks that look like this? Kind of at the edges of streams and on the beach, where these high energy environments can move these things and crash these things together, and they slowly round as they continue to collide. So this is kind of a chart that just shows basically all of that kind of stuff. Rounded versus angular is the opposite of that. Well sorted, poorly sorted, grain size. So all of these things can tell us well, first off, the material itself can tell us about the original source rock, the size of the material, the roundness of the material, the sorting of the material. All of that helps us to infer furthermore about the environment in how this was the sediment was transported, as well as the depositional environment where this stuff was deposited to eventually lithify and turn into sedimentary rocks. So they tell a good story of the past. Now, if we're able to date material in sedimentary rocks, maybe there's some igneous intrusions or any number of things, then that helps us to put together the geologic past and start to tell the story of Earth. So let's go ahead and pause there. When we come back, we'll look at sedimentary structures. These are kind of cool. See you back here in just a second.